July 10th, 1893, Chicago World's Fair. The Palace of Electricity, America's grand showcase of electrical innovation, erupts in flames that kill 16 people, including 12 firefighters trapped beneath collapsing steel towers. European trained engineers had dismissed electrical safety testing as unnecessary expense. Insurance inspectors had warned of faulty wiring for months, but established wisdom said systematic testing was too costly, too complex, too different from centuries of proven European methods. Through the smoke and chaos, a 25-year-old MIT electrical engineer named William Henry Merrill witnesses something that changes everything. Not just the deadly fire, but the reason it happened. American electrical installations were built using European craft traditions that worked for gas lighting but failed catastrophically with electrical current. While European engineers continued specifying cloth insulation sealed with varnish and tar, Merrill began developing something radically different: scientific testing, measurable standards, performance-based specifications that would create electrical wire so superior it would remain safe for nearly a century. What Merrill discovered in his third-floor laboratory would prove that American innovation could surpass European tradition in ways no one imagined possible. 9 months after the Palace of Electricity disaster, William Henry Merrill stood in the cramped third-floor laboratory above the Chicago Fire Underwriters Association patrol station, holding what looked like ordinary paper between a pair of metal tongs. The sample had arrived that morning with bold claims printed on the manufacturer's letterhead: non-absorbent and non-combustible asbestos paper, guaranteed fireproof insulation. European electrical engineers had been recommending asbestos-based materials for decades, trusting manufacturer specifications without independent verification. Merrill intended to find out if their trust was justified. He lit a Bunsen burner and adjusted the flame to precisely 400 degrees Fahrenheit, the temperature at which most electrical fires began consuming surrounding materials. The asbestos paper sample, clamped in metal tongs, entered the flame zone. Nothing happened. The paper remained intact, refusing to ignite even under direct flame contact. Merrill made careful notes in his leather-bound testing journal. Sample maintained structural integrity under sustained heat exposure. The manufacturer's combustibility claims appeared accurate. Next came the absorption test. Merrill submerged an identical paper sample in a beaker of distilled water, timing the saturation process with his pocket watch. Within 30 seconds, the supposedly non-absorbent material had soaked through completely, transforming from rigid sheet to soggy pulp. Water dripped steadily from the saturated sample as Merrill recorded his observations. Material absorbs water readily despite manufacturer claims. Absorption rate: complete saturation in under 1 minute. The asbestos paper might resist fire, but it failed catastrophically as electrical insulation the moment moisture entered the equation. This contradiction revealed the fundamental flaw in European electrical engineering methods. For centuries, European craftsmen had selected materials based on traditional applications and manufacturer representations, rather than systematic testing under actual operating conditions. They specified materials that worked perfectly for gas lighting installations, where heat tolerance mattered more than moisture resistance, but proved dangerous in electrical applications where both factors were critical. Merrill was documenting a pattern that would define his entire career: the gap between claimed performance and measurable reality. The Chicago Fire Underwriters Association had provided Merrill with $350 in testing equipment and a 5-year funding commitment, making his laboratory the first independent electrical safety testing facility in the United States. Unlike European testing houses that focused on material composition and manufacturing quality, Merrill designed tests that simulated real-world installation conditions. His equipment included calibrated heating devices, electrical load testing apparatus, environmental chambers for humidity and temperature variation, and precision measuring instruments for material thickness and electrical resistance. By December of 1894, Merrill had completed 75 electrical safety tests on components ranging from wire insulation materials to electrical fixtures and switching devices. Each test followed identical methodology: establish baseline performance specifications, subject samples to controlled stress conditions that matched or exceeded typical installation environments, measure performance degradation over time, and document failure modes under systematic observation. The results consistently contradicted European engineering assumptions about material performance and safety margins. The breakthrough came during tests of rubber insulation compounds in March of 1895. European electrical engineers had dismissed rubber as unsuitable for permanent installations, claiming it degraded too quickly under electrical load and temperature stress. Merrill's testing revealed the opposite. When properly compounded with sulfur and carbon additives, then manufactured to precise thickness specifications, rubber insulation outperformed every traditional material under sustained electrical load conditions. Unlike cloth insulation that frayed and created fire hazards, or varnish-sealed coverings that cracked and exposed dangerous conductors, properly formulated rubber maintained integrity for thousands of hours under continuous electrical stress. The technical specifications Merrill developed for rubber insulation were revolutionary in their precision. Minimum thickness requirements measured in thousandths of inches rather than approximate fractional measurements. Heat resistance testing at specific temperatures for defined time periods rather than general flame exposure. Electrical breakdown voltage thresholds determined through controlled laboratory testing rather than theoretical calculations. Long-term aging tests under controlled environmental conditions that simulated decades of actual installation conditions. These specifications enabled American wire manufacturers to produce electrical components with predictable, measurable safety characteristics for the first time in electrical engineering history. By 1898, Merrill's laboratory had tested over 1,000 electrical components and materials, establishing performance data that no European testing facility could match. The results formed the foundation for UL's first published list of approved electrical fittings and devices, complete with distinctive labels that identified products meeting scientific safety standards. American electrical contractors could now specify components based on verified performance data rather than manufacturer claims or European craft traditions. The transformation was measurable. Buildings wired with UL-approved components showed electrical fire rates of less than 0.02% compared to over 2% for installations using uncertified materials and traditional European methods. Insurance companies that had initially dismissed Merrill's testing as expensive and unnecessary began requiring UL certification for reduced premium rates. The systematic, scientific approach that European engineers had rejected as too complex and too costly had produced electrical safety improvements that were impossible to ignore. Merrill's third-floor laboratory had become the center of a quiet revolution in American electrical engineering, proving that scientific methodology could surpass centuries of European craft traditions through systematic testing and measurable standards. The young engineer who had witnessed preventable deaths at the World's Fair had created the foundation for electrical safety standards that would protect American buildings for generations to come. In January of 1903, Merrill faced a challenge that would define the future of American safety engineering. The National Fire Protection Association had requested UL develop the first comprehensive safety standard for tin-clad fire doors, but European fire safety experts insisted that door specifications should focus on material composition rather than performance under actual fire conditions. Traditional European methods specified minimum metal thickness, specific alloy compositions, and manufacturing techniques based on centuries of metalworking tradition. Merrill proposed something radically different, performance-based standards that measured how doors actually behaved when exposed to standardized fire conditions. The technical implications were revolutionary. Instead of specifying that fire doors must contain particular metal alloys or achieve certain thickness measurements, Merrill's standard would require doors to withstand specific temperature exposures for defined time periods while maintaining structural integrity and preventing flame penetration. European fire safety engineers argued this approach was unnecessarily complex and expensive, requiring specialized testing equipment that most manufacturers could not afford. They preferred traditional craft-based specifications that allowed manufacturers to follow established metalworking practices without independent verification. Merrill constructed a testing apparatus unlike anything European fire safety facilities possessed. The fire testing chamber could generate controlled temperatures up to 1800 degrees Fahrenheit, with precision thermocouples measuring temperature distribution across door surfaces at 15-second intervals. Standardized fire exposure protocols subjected doors to temperature curves that matched real building fire conditions rather than theoretical flame exposure. Structural integrity measurements tracked door warping, joint separation, and hardware failure under sustained heat stress. The testing methodology produced quantifiable data about door performance that European craft-based methods could never provide. The first standard for safety publication in 1903 established principles that would transform American manufacturing. UL Standard No. 1 specified performance requirements rather than material compositions, creating a framework that enabled innovation while ensuring safety. Manufacturers could use any materials or construction methods that achieved the required performance thresholds, encouraging technological advancement rather than adherence to traditional practices. European fire door standards continued specifying particular metal alloys and manufacturing techniques, limiting innovation and preventing cost-effective improvements. American manufacturers responded to performance-based standards by developing innovative construction techniques that European competitors could not match. Instead of relying on expensive metal alloys to achieve fire resistance, American companies created composite door designs using multiple materials optimized for specific performance characteristics. Steel cores provided structural strength, ceramic insulation materials managed heat transfer, and specialized gasket systems prevented smoke and flame penetration at door edges. These designs achieved superior fire protection at lower costs than traditional European solid metal construction. The manufacturing advantages became apparent within 2 years of the standard's publication. American fire door manufacturers could produce doors meeting UL performance requirements at 60% of the cost of equivalent European doors, while achieving superior fire resistance ratings. European manufacturers attempting to compete in American markets faced the choice of investing in expensive testing equipment to verify their products met UL standards, or accepting reduced market access for uncertified products. Most chose to modify their products to meet American performance requirements rather than lose market opportunities. By 1906, UL had established the Label Service Program that revolutionized American manufacturing quality control. Rather than relying on single product testing, the Label Service required ongoing factory inspections and periodic retesting to ensure consistent product quality. American manufacturers could display the distinctive UL mark only when their production processes maintained the performance standards verified through continuous monitoring. This systematic approach to quality assurance exceeded anything European certification systems offered. The Label Service created competitive advantages that extended far beyond fire safety. American manufacturers with UL certification could guarantee product performance to customers, reducing warranty costs and liability concerns. Insurance companies offered reduced premiums for buildings using UL-listed products, creating financial incentives for specifying American-made components. Export opportunities expanded as international customers recognized UL certification as evidence of superior American manufacturing quality. European attempts to compete with American performance-based standards proved unsuccessful. Traditional European certification methods focused on manufacturer reputation and craft guild memberships rather than systematic performance verification. When European fire door manufacturers submitted products for UL testing, failure rates exceeded 70%, demonstrating that craft-based construction methods could not achieve the consistent performance that American manufacturing processes delivered. European fire safety officials criticized UL standards as unnecessarily stringent, but their complaints could not overcome the measurable performance advantages American products demonstrated. The transformation accelerated when major insurance companies began requiring UL certification for commercial fire safety equipment. European manufacturers lost access to lucrative American markets unless their products achieved UL performance standards, forcing them to either invest in American-style testing capabilities or abandon competition with American manufacturers. The performance-based standards that European engineers had dismissed as too expensive and too complex had created insurmountable competitive advantages for American manufacturers. By 1910, the standard for safety concept had expanded beyond fire doors to encompass electrical equipment, mechanical systems, and building materials. Each new standard followed Merrill's performance-based methodology, creating measurable requirements that encouraged innovation while ensuring safety. American manufacturers had learned to design products that exceeded performance thresholds rather than simply meeting minimum material specifications, establishing technological leadership that European competitors could not match. The systematic approach to safety standards that began with tin-clad fire doors had become the foundation for American manufacturing superiority across multiple industries, proving that scientific methodology could surpass traditional craft practices through measurable, repeatable performance verification. The emergency telegram reached Merrill's office at 7:32 on the morning of February 15, 1911. The Riverside Manufacturing Company in Detroit had suffered a catastrophic electrical fire that killed 3 workers and destroyed $40,000 in machinery, despite using components that carried UL certification labels. Within hours, similar reports arrived from Philadelphia, Cleveland, and Buffalo. Buildings equipped with UL-certified electrical systems were burning at rates that approached non-certified installations, threatening to destroy the credibility that Merrill had spent 17 years building. The Chicago Tribune's morning edition carried a headline that summarized the crisis perfectly. "Scientific safety testing fails. UL standards, no better than European methods." Insurance executives who had reluctantly accepted UL certification requirements now questioned whether systematic testing provided any real advantages over traditional risk assessment methods. The Boston Board of Fire Underwriters, which had rejected Merrill's original safety proposals in 1893, issued a statement suggesting that American performance-based standards had proven no more reliable than European craft traditions. Merrill assembled a team of 12 investigators within 72 hours, dispatching them to every reported fire site, with instructions to document electrical system conditions rather than assume component failure. The investigation methodology followed the same systematic approach that had established UL's original standards: measure actual conditions, document physical evidence, and analyze failure patterns through controlled comparison rather than theoretical speculation. European fire investigation techniques relied on expert opinion and visual inspection, but Merrill's team carried electrical testing equipment that could measure conductor resistance, insulation breakdown voltages, and installation quality with scientific precision. The first breakthrough came at the Detroit manufacturing facility, where investigator Thomas Morrison discovered that the building's electrical system contained UL-certified components installed alongside uncertified wiring that predated the fire by 8 years. The certified components had performed exactly as specified, maintaining insulation integrity and preventing electrical faults even under extreme heat exposure. The fire had originated in uncertified junction boxes where cloth-insulated wiring had deteriorated to the point where bare conductors created sparking conditions. The UL-certified portions of the electrical system had actually prevented the fire from spreading to other building sections. Similar patterns emerged at every investigation site. Buildings experiencing electrical fires contained combinations of UL-certified and uncertified components, with fire origins consistently traced to the uncertified portions. Contractors seeking to reduce installation costs had used UL-certified components for visible portions of electrical systems while installing cheaper, uncertified materials in wall cavities and ceiling spaces where building inspectors rarely examined installation quality. The systematic failure of uncertified components created conditions that even properly installed UL-certified materials could not prevent. The statistical analysis that Merrill completed in June of 1911 provided definitive evidence that contradicted the newspaper criticism. Buildings with electrical systems consisting entirely of UL-certified components showed fire rates of 0.02%, maintaining the safety record that had been established over 15 years of systematic testing. Buildings containing combinations of certified and uncertified components experienced fire rates of 1.8%, approaching the rates associated with entirely uncertified installations. The data demonstrated that UL certification provided exceptional safety performance, but only when applied systematically throughout entire electrical systems rather than selectively to reduce costs. The investigation revealed a fundamental difference between American and European electrical installation practices. European electrical contractors followed guild traditions that emphasized craft skill in working with whatever materials were available, adapting installation techniques to accommodate material variations in quality and consistencies. American contractors working with UL-certified components could rely on standardized performance characteristics that enabled systematic installation methods with predictable safety outcomes. The European approach required individual expertise to compensate for material uncertainty, while the American approach eliminated material uncertainty through systematic testing and standardization. Insurance company claims analysis confirmed the investigation findings with overwhelming statistical evidence. Buildings with complete UL-certified electrical systems generated insurance claims averaging $12 per year per $1,000 of coverage, compared to $138 per year for buildings with uncertified systems. The difference represented more than 11 times greater safety performance for systematically certified installations. Claims processing. Costs were also significantly lower for UL-certified systems because fire causes could be determined quickly through systematic investigation rather than lengthy expert opinion processes. The crisis that had threatened to destroy UL's credibility instead provided the most convincing demonstration of systematic safety testing's effectiveness. European fire safety experts who had criticized American performance-based standards as unnecessarily complex were forced to acknowledge that the statistical evidence supported systematic certification over traditional craft-based approaches. Major insurance companies that had questioned UL requirements during the crisis began requiring complete system certification rather than accepting partial compliance with safety standards. By 1912, the investigation's findings had transformed American electrical installation practices. Building codes in major cities required UL certification for all electrical components rather than permitting selective use of certified materials. Electrical contractors discovered that systematic use of certified components reduced installation time and warranty costs compared to working with materials of uncertain quality and performance. The standardized performance characteristics of UL-certified components enabled contractors to develop efficient installation methods that were impossible with traditional European materials. The crisis had provided definitive proof that systematic safety testing delivered measurable advantages over traditional engineering approaches, establishing the foundation for American electrical infrastructure that would prove superior to European systems for decades to come. The young engineer's systematic methodology had survived its greatest test and emerged with evidence that no critic could dispute. When President Wilson's call for industrial mobilization reached Merrill in April of 1917, the challenge seemed impossible. The United States needed to transform from peacetime production to wartime manufacturing capacity within months, requiring electrical infrastructure that could power munitions factories, shipyards, and aircraft production facilities operating at unprecedented scales. European allies had spent 3 years building their wartime electrical systems, often suffering catastrophic explosions when inadequate wiring caused fires in facilities storing high explosives. American manufacturers would need to achieve in months what Europeans had struggled to accomplish safely over years. The War Industries Board appointed Merrill as head of the Fire Prevention Section at a salary of $1 per year, recognizing that his systematic safety testing methodology represented the only proven approach for preventing industrial disasters during rapid expansion. Traditional European engineering methods relied on individual expertise and craft traditions that could not scale to meet wartime production demands. American industrial capacity would depend on systematic standards that enabled rapid construction of safe electrical systems by contractors with varying skill levels. Merrill's first assignment required auditing electrical installations at 2,444 munitions plants across 17 states within 6 months. European munitions facilities had experienced over 300 electrical fires during their first year of expanded production, with explosions at plants in Birmingham, Sheffield, and Toulouse killing hundreds of workers and destroying months of production capacity. American munitions manufacturers demanded electrical systems that could operate safely under conditions that exceeded any civilian installation requirements. Continuous high-power loads, explosive atmosphere exposure, and accelerated construction schedules that eliminated traditional safety margins. The technical specifications Merrill developed for wartime electrical installations represented a revolutionary advance over European methods. Instead of relying on individual inspector judgment, American standards specified measurable performance requirements for every component in munitions facility electrical systems. Wire insulation had to withstand electrical loads 50% higher than normal operation for continuous periods exceeding 8,000 hours. Junction boxes required explosion-proof construction that contained internal detonations without propagating to surrounding equipment. Electrical switching equipment needed automatic fault detection systems that disconnected power within milliseconds of detecting dangerous conditions. The systematic approach produced immediate results that European munitions experts had considered impossible. American contractors could install electrical systems in new munitions facilities within 30 days using standardized components and systematic installation procedures. European contractors required 3 to 6 months for comparable installations, relying on custom fabrication and individual craftsmanship that delayed production startup. The time advantage enabled American munitions production to reach full capacity months ahead of schedule, providing artillery shells and explosives that proved decisive in European battlefields. Safety performance exceeded even Merrill's optimistic projections. American munitions facilities operating under UL electrical standards experienced 0 electrical fires during the first 18 months of wartime production, compared to ongoing explosion problems at European facilities using traditional installation methods. The DuPont Company's explosive manufacturing complex in Delaware processed more high explosives than all European facilities combined while maintaining perfect electrical safety records. Insurance companies that had initially charged premium rates for munitions facility coverage reduced rates below peacetime levels when UL certification was verified throughout electrical installations. The wartime testing program expanded UL's technical capabilities beyond anything European testing facilities could match. Merrill's laboratories developed high-power electrical testing apparatus that subjected components to electrical loads equivalent to continuous operation under maximum wartime production conditions. Environmental testing chambers simulated the corrosive chemical atmospheres present in munitions manufacturing, verifying that electrical components maintained safety performance when exposed to explosive vapors and chemical contamination. Mechanical stress testing ensured that electrical equipment could withstand the vibration and shock conditions created by heavy industrial machinery operating at wartime production rates. American electrical component manufacturers responded to wartime requirements by developing products that surpassed European specifications by substantial margins. Westinghouse Electric created explosion-proof electrical enclosures that contained internal detonations exceeding twice the force that European safety codes required. General Electric developed automatic circuit protection systems that responded to electrical faults in microseconds rather than the milliseconds that European equipment required. These innovations provided safety margins that enabled American munitions production to operate at power levels that European facilities could not achieve safely. The transformation of American electrical manufacturing during wartime created permanent competitive advantages that extended far beyond military production. Manufacturers that had invested in systematic quality control to meet wartime UL requirements discovered that peacetime products could be produced at lower costs with higher reliability than traditional craft-based methods provided. Export opportunities expanded as international customers recognized American electrical equipment as superior in both safety performance and manufacturing consistency. By Armistice Day in 1918, Merrill's systematic approach to electrical safety had enabled American industrial production that exceeded the combined output of all European allies during their peak wartime capacity. American munitions facilities had produced artillery shells, explosives, and military equipment in quantities that overwhelmed German industrial capacity while maintaining safety records that European manufacturers could not match. The electrical infrastructure that powered this production used systematic standards that eliminated the craft traditions and individual expertise requirements that limited European manufacturing scalability. The wartime vindication of systematic safety testing established principles that would guide American industrial development for decades. Performance-based standards that enabled rapid scaling of production capacity had proven superior to traditional European methods that relied on individual craftsmanship and established practices. The young engineer who had proposed systematic electrical safety testing after witnessing preventable deaths at the 1893 World's Fair had created the foundation for American industrial dominance that would shape global manufacturing for generations to come. By 1920, the statistical evidence was overwhelming. American buildings constructed with systematic UL electrical standards showed residential fire rates 85% lower than structures using traditional European wiring methods. The rubber insulation standards that Merrill had developed in his third-floor laboratory 26 years earlier had created electrical systems so robust that buildings wired during the 1890s continued operating safely without replacement or major maintenance. European electrical installations from the same period required complete rewiring every 15 to 20 years due to insulation deterioration and component failures. The transformation extended beyond individual buildings to reshape entire American cities. Detroit's automotive manufacturing district operated on electrical infrastructure that carried power loads exceeding the capacity of entire European industrial regions while maintaining safety records that European engineers considered impossible. The systematic standardization of electrical components had enabled American manufacturers to design power distribution systems that scaled efficiently from small workshops to massive industrial complexes without compromising safety performance or increasing maintenance requirements. International recognition of American electrical superiority became undeniable when European governments began requiring UL certification for electrical equipment used in reconstruction projects following the war. British electrical contractors discovered that American manufactured components specified to UL performance standards could be installed by workers with basic training, while traditional European electrical work required craftsmen with years of specialized experience. French industrial facilities rebuilt using American electrical standards achieved production capacity that exceeded their pre-war output by 40% while operating with improved safety records. The economic implications transformed global trade relationships in ways that European governments struggled to understand. American electrical equipment manufacturers could produce components meeting precise performance specifications at costs 60% below equivalent European products while delivering superior safety and reliability characteristics. European manufacturers attempting to compete in international markets faced the choice of investing in American-style testing facilities to verify product performance, or accepting reduced market access for uncertified products that could not match American quality standards. Merrill's systematic approach had evolved into something unprecedented in engineering history, a comprehensive methodology for translating scientific principles into measurable industrial standards that enabled technological innovation while ensuring safety performance. The techniques developed for electrical component testing had expanded to encompass mechanical systems, building materials, chemical processes, and manufacturing equipment. American industrial facilities could specify components with known performance characteristics and predictable service life, enabling systematic maintenance planning and replacement scheduling that European facilities could not achieve. The rubber insulation formulations that had emerged from Merrill's early laboratory work represented a paradigm shift in materials engineering. European electrical installations continued using cloth, varnish, and tar-based insulation systems that required regular inspection and frequent replacement due to environmental degradation. American rubber insulation compounds, manufactured to precise chemical specifications and thickness requirements, maintained electrical properties for decades under conditions that destroyed traditional materials within months. Buildings wired in 1905 with UL-certified rubber-insulated cable operated safely in 1925 without electrical system modifications. The longevity advantage created economic benefits that compounded over time. American building owners could amortize electrical installation costs over 30 to 40-year periods, while European property owners faced electrical system replacement every 12 to 15 years. The difference enabled American commercial and industrial development at scales that European capital markets could not support efficiently. American cities could invest in electrical infrastructure expansion, knowing that systematic standards guaranteed long-term performance, while European cities faced ongoing maintenance costs that limited expansion capabilities. Technical education institutions worldwide began adopting American systematic testing methodologies as the standard for engineering education. European universities that had taught electrical engineering through craft tradition and apprenticeship systems could not prepare graduates to work with the precision measurement and systematic analysis techniques that modern electrical systems required. MIT's electrical engineering program, which had trained Merrill and dozens of engineers who established systematic testing procedures, became the model for technical education programs in countries seeking to modernize their electrical infrastructure. The international copying of American systematic standards validated the fundamental principles that Merrill had established in his Chicago laboratory. Performance-based specifications that measured actual component behavior under controlled conditions produced more reliable results than traditional methods based on material composition. In July 10, 1893, Chicago World's Fair. The Palace of Electricity, America's grand showcase of electrical innovation, erupts in flames that kill 16 people, including 12 firefighters trapped beneath collapsing steel towers. European trained engineers had dismissed electrical safety testing as unnecessary expense. Insurance inspectors had warned of faulty wiring for months, but established wisdom said systematic testing was too costly, too complex, too different from centuries of proven European methods. Through the smoke and chaos, a 25-year-old MIT electrical engineer named William Henry Merrill witnesses something that changes everything. Not just the deadly fire, but the reason it happened. American electrical installations were built using European craft traditions that worked for gas lighting but failed catastrophically with electrical current. While European engineers continued specifying cloth insulation sealed with varnish and tar, Merrill began developing something radically different: scientific testing, measurable standards, performance-based specifications that would create electrical wire so superior it would remain safe for nearly a century. What Merrill discovered in his third-floor laboratory would prove that American innovation could surpass European tradition in ways no one imagined possible. 9 months after the Palace of Electricity disaster, William Henry Merrill stood in the cramped third-floor laboratory above the Chicago Fire Underwriters Association patrol station, holding what looked like ordinary paper between a pair of metal tongs. The sample had arrived that morning with bold claims printed on the manufacturer's letterhead: